is that we allow the speaker to finish talking and then take all the questions at the end. Because it's online, otherwise it becomes a little difficult to manage. So with that said, I guess the record button is on. So I'll introduce the speaker that we have today. This is Alfonso Ngan from University of Birmingham. He's joined this particular University of Birmingham, the last year sometime as its 125th anniversary chair. And he's also a Royal Society Wolfson Fellow and Director of the Institute of Advanced Studies at the University of Birmingham. He's also an alumni from this institute where he did his PhD in 1992 after obtaining his BSc degree from the University of Hong Kong in 89. He then joined the University of Hong Kong as a faculty after completing his postdoctoral training at Oxford University. And in March 2025, like I said, he returned to University of Birmingham. He is very well known for his work in nanomechanics and in novel stimuli response materials and smart actuation, which he's recently been working on, and including applications to biological systems. His research has related to many awards, the Rosenheim Medal from the Institute of Materials, Minerals and Mining, UK, Croucher Senior Research Fellowship, and many more, like you can read from his bio here. Professor Ngan is visiting IIT Bombay as a Royal Society Yusuf Hamid Fellow, a visiting fellow for the few weeks that we are having him here. He has accepted to give this seminar to us on the statistical mechanics of dislocations in high-entropy alloys. With that formal introduction, I would request Alfonso to take over and present his work.
All right, thank you very much, Jaya, for the very nice introduction, and very glad to be here in this webinar to share my research to this very distinguished group of people in India. I am now working at the University of Birmingham. The university formally became a university in 1900. So last year, there was a round of recruitment of chair professors, which was called the 125th anniversary chair. I was lucky enough to be recruited as the first holder of this chair in the College of Engineering and Physical Science. And actually, Birmingham, being close to the birthplace of the Industrial Revolution, it was basically a place where the subject of physical metallurgy was pioneered. So here we are looking at some of the very familiar names in physical metallurgy, including the very first professor of metallurgy in the UK, Thomas Turner. And the department in Birmingham still offers yearly a Best PhD Thesis Award under his name. And I was fortunate enough that when I graduated 30-odd years ago, I was also awarded this award. And of course, we all know Alan Cottrell, Cottrell locking, Cottrell atmosphere, Robert Kahn, Pals-Net-Barrow for the singing, dancing Pals-Net-Barrow model for dislocation friction, Jock Eshelby inclusion, Ray Smallman, my own supervisor, who had done pioneer work on Stackingford tetrahedra. He was actually a student of Alan Cottrell. And for many of you in this community working on fracture, of course, John Knott was also a famous name. Of course, when we talk about physical metallurgy, dislocation is a very, very important topic. And many of the pioneers I just mentioned, and actually all over the world, they have done great work on dislocation. So this talk is about dislocations. In particular, we will pay a lot of attention to this line tension, which is the elastic energy per unit length, or of the order of mu b squared. Due to the line tension, dislocations tend to stay short and tend to stay straight. So the line tension obviously is to shorten the length of dislocations. So this concept I will keep going back later on in this course. So first of all, let me give a quick introduction to complex concentrated alloys. Because I understand that the audience today can be diverse. So what are CCAs? What are complex concentrated alloys? These are alloys with 3 or more elements. If they contain 5 elements, they would be called high entropy alloys. If they contain 3 elements, they will call medium entropy alloys. And these elements are in more or less equal atomic ratio. And the interesting thing is that most of the time, these alloys would have the atomic species arranged randomly. So down to the solid level, the 3 or 5 elements will be distributed randomly in space. Or if you give the alloy some proper treatment, heat treatment, certain short-range ordering can be developed. So certain segregation of elements may happen. So why are CCAs fascinating to physical metallurgists? First, as I have mentioned, the strength in metals and alloys in the traditional understanding is governed by dislocation interactions with the crystal lattice, and therefore we have the Parsnip-Barrow model in the subsequent developments, or with solutes and also precipitates if you have two-phase or multi-phase systems. So in pure metals or dilute alloys, the typical dislocation interactions are of these 3 types in below. You could have dislocation core interaction with the lattice. Let's say if the dislocation core is not planar, then you would have to overcome this non-planar interaction, and therefore usually we would have the king pair mechanism. So that would be a critical stage for movement of dislocation in high purity metals. And if you have solute, of course, the solute will interact with the elastic field and also the core chemically with the core, and that would also obstruct dislocation motion. Or if you have two-phase precipitates, then you have the well-known Orwin looping. So these are all well-known in physical metallurgy. However, for complex concentrated alloys, our understanding of strengthening would need a completely new look, because dislocations move in a concentrated solute field of fluctuating local atomic environments, which are not highly concentrated, which are not highly focused into, for example, precipitates or individual solid atoms. And usually the interaction also happens in a stochastic, highly stochastic manner. So these conventional understanding may not play a very important role, but then we need a very completely new look into the issue. So this was a paper we published a few years back, and this just illustrates the type of defect-induced atomic environments in this case a medium entropy alloy, so involving 3 elements: nickel, cobalt, and chromium. So we may be talking about, well, this is an FCC system, and the stacking fault energy is actually very, very low. So the a unit half 1O dislocation would dissociate widely into 2 shortly parcels with a stacking fault in between. So we will obviously have Suzuki segregation, where if you look at this plot over here, which may be too small to be seen, but I'll tell you the result. The nickel of the 3 elements here tend to segregate on the stacking faults. So this is one type of segregation that would occur with a dissociated dislocation, with a stacking fault in this dissociated dislocation. And for either of the 2 shortly partials, we may also have the Cottrell segregation as well. So in this case, some elements will segregate to the dislocation core. So this is known as the Cottrell segregation. We may also have the so-called Fisher strengthening effect, which is when a dislocation moves it may destroy the short-range ordering. So by breaking the short-range ordering, there will be some resistance arising from that breakage, and that would cause certain strengthening as well. So some of these CCAs would exhibit dynamic strain aging. So during deformation, especially at lower speeds, lower deformation rate, there will be stress jumps. And the stress jumps are on the order of a few dozen or about 100 megapascal. So in this paper, we analyze out of these various mechanisms, which one is more dominating. And for this particular alloy, it turns out that the Suzuki, this stacking fault segregation, turns out to be the most dominating, which is the yellow color in here. So this in this bar, we are breaking down the contribution of the several mechanisms. So the yellow contribution is from the Suzuki. And then the second major one would be from Cottrell. And then Fisher turns out to be a very small contribution. Well, that's only for this alloy. For other alloys, the situation may not be the same. Okay, so the motivation of this talk is that because of such dislocation, solute atmosphere interaction, as I said before, we need a completely new understanding on what's going on in these CCAs, complex concentrated alloys. Specifically, I will be explaining why a statistical mechanics perspective is of value here, or is actually very appropriate here in describing dislocations in these CCAs. And I'll also talk about a type of quite interesting transition known as the Larkin transition. And then for CCAs, the Larkin transition is distinctively different from that in pure metals and dilute alloys. And I'll talk about the details later on. So I'll be focusing on these two aspects in this talk. Well, we don't need to pay too much attention to the maths in here, but I just want to show you that conventionally or before my group started our line of work, as we analyzed the literature, there have been models where authors try to model dislocation resistance in CCAs. But then these models are often what we call very intensive, and they come with strong assumptions. So I highlight one example in here. So this is a group based in Hong Kong. By the way, Dave Strolowitz was my previous dean before I relocated to Birmingham. So I know him very well. A great scientist, high respect for him. And here they take the original Powers-Nabarro model, which everybody knows that it could be written in this form in textbooks, but then they give perturbation to this D, which is the interplanar spacing. So the perturbation is to account for the lattice distortion when the system now has different elements of different sizes. So they subject this D, this interplanar spacing, to a normal distribution. And after some Fourier transform analysis, they sort of concluded that the Power stress would be elevated by a factor, which is this term into here. However, as we calculated the exact value of this term, it turns out that this value is very, very small, as you can see, unless this delta, which is the lattice distortion, becomes really large. But in the usual range that we are talking about, 10% or below, you are talking about an increment due to lattice distortion of only by 10%, 20%. So this is a very small contribution. So although the model is mathematical appealing, we do not think this is important. We have these very strong assumptions. So that's one of the intensive models existing in the literature. Another one would be, for example, from the group of Bill Curtin, where they look at well, they basically focus on the solute dislocation interaction, but then they make use of the solute straight dislocation interaction in the classical literature and bend that into an effective medium to describe the CCA. So again, the model is mathematically appealing, lots of equations in that paper if you really read into that. But it comes with a lot of assumptions, basically strong assumptions, particularly the fact that in the CCA where every solute can be regarded as, or every atom can be regarded as solute as well as solvent. So how are you going to specifically define which atom is solute and which atom is solvent? So this is the case that a very strong assumption is involved. So I'm going to talk about the fluctuation nature of dislocations in CCA due to the local atomic environment. So just to give you some ideas of what sort of fluctuations we can be talking about. So in general, let's say if we take the leading shortly of an FCC dislocation into consideration. So as this dislocation moves forward, it will trace a new area of stacking fault, which is called complex stacking fault. And so the resistance of that movement can be well represented by the value of this fault energy gamma. For the case of the leading Shockley partial, as I said, the complex stacking fault would be the main resistance. In the case of the trailing, when the trailing dislocation marches forward, it annihilates the complex stacking fault, but it generates an antiphase boundary. In the case of an alloy where ordering could happen. So in this case, the effective value of the fault energy acting against the motion of the trailing partial would be the APB energy minus the CSF energy. So that would be the resistance for the trailing. For the leading, it will be just the CSF energy alone. So it is either the CSF or the APB minus CSF fault energy, they'll be representing the shear resistance to dislocation or Shockley dislocation motion other than the Powell stress. However, in a CCA, the fault energy is not constant over the slip plane because we could have short-range order developed, or even without short-range order developed down to single atomic level. If you look at different points over the slip plane, the fault energy would vary. So in general, we would have a profile as represented by this temperature map. So where the color scale represents the magnitude of the fault energy. For the trailing case, it will be the APBE minus CSFE. And for the leading partial, it will be just the CSFE alone. So as you can see, this is the slip plane, and then the fault energy is not a constant value. It fluctuates spatially. And overlaid on top of this profile, the black lines are images of one partial gliding through the slip plane from the left to the right. So you can see that the dislocation is always wiggling as it glides through this fluctuating gamma landscape. Obviously, this is due to the interaction between the dislocation and the solute atmosphere in the slip plane, which is represented by the fluctuating gamma. And this is some real, not real, but molecular dynamics simulation. So this is CCA, this system, vanadium, cobalt, nickel at 5 Kelvin. And as you can see, the two partials, as they move, they always wiggle in shape. While if you look at a pure metal, so this is just iron, again at a low temperature, also 5K or so, when it moves, moves via generation of a kink pair and propagation of kink pair. So most of the time, the dislocation is straight. The only fluctuation would be kink, which is one atomic step in height, and then propagation of that. So this is a big difference between dislocation behavior in a CCA and in a pure metal or dilute alloy. And of course, the reason for the interaction would be some of the sites. So in the case of the vanadium, cobalt, nickel, the vanadium is the bigger atom. So the vanadium sites tend to interact strongly or pin more strongly the dislocation. So here we have some direct evidence of that. So here, first of all, the left-hand side, A, is the MD simulated result. So through the MD simulation, and also we use Monte Carlo to stabilize the structure, to enable the structure to adapt to an equilibrium. We found that in this case, the dislocation cores are usually segregated with vanadium. And BC would be experimental results. So here we have a few dislocations. And as we do a line scan across them, so whenever you see, whenever you detect the chemistry at a dislocation site, you'll see a little bump in the vanadium content. So that more or less confirms the MD-MC result. So it's the segregation of vanadium in this case, which would pin the dislocation, but then the segregation doesn't occur uniformly along a dislocation length on the slip plane, and therefore the dislocation would tend to be wiggling as it moves on the slip plane. And there are other evidences in other systems. So in this case, we have the cobalt, chromium, nickel system, where in this case, the stronger pinning points would correspond to some special atomic clustering, such as clustering where you have more cobalt and chrome pairs. So these are, of course, down to very localized chemistry that are the pinning sites. So in the next part, we are going to use machine learning from molecular dynamics generated data to learn objectively which factors in the alloy contribute more to lowering the dislocation mobility. So if you run an MD simulation, so this is typically how you run an MD simulation, you generate a block and then you pass a dislocation, apply some stress. Dislocation may be dissociated into two partials like this. And you can regenerate the cell and rerun this many times. So out of many attempts, you end up with a lot of data. So these data could be local fault energies. So the very localized pixel point, for example, you can back out what is the local fault energy, be it the CSFE for the leading partial or the difference between APB and CSF for the trailing partial. So you can back out the local fault energy, look at that distribution, for example, or you can analyze the dislocation core using, for example, the 9 tensor plot, and then you can analyze the width of the partial dislocation. So that will be another type of data you can generate from the MD simulation. Or you can, from the stick slip motion of the dislocation, you can back out their, let's say, the velocity, which is shown in here. The profile is shown in here. The velocity, the probability profile is shown in here. So you can generate a lot of data. So as I said previously, we want to understand which of these factors are more dominating in controlling the dislocation mobility reflected in terms of the dislocation velocity. So we found that it's actually this purple bar, which is more dominating. So this is like an ablation study. So we have a number of factors. We knock out we knock out the factors one by one. to see whether the machine learning model, to understand how well the machine learning model will predict the velocity. So as you can see, the highest prediction accuracy comes from the factors where we have the fault energy as well as the core shape or core width of the dislocation. So both the fault energy and the Powell's barrier are controlling, which of course in hindsight this will be common sense, but we are able to prove that objectively from a lot of MD data. So we now would agree that, or we would appreciate that dislocations in a CCA are always wavy. So what can we go from there to try to predict the critical resolved shear stress, for example, and especially without strong assumptions, without making any strong assumptions like a particular interaction law with a solute or with the original Powell's-Nabarro model. So we look at a wavy dislocation like this and look at two dwell states. So we look at this shape, and then in the next time instant, the dislocation has migrated to a new shape. So xi and xi plus 1 will be the two shape functions of the dislocation, where x is this direction. So we are talking about treating the dislocation as a wave, while the x would be the displacement, all right, while y is the variable along the length of the dislocation. So between these two states, we can write down this equation as an energy balance. So the term on the left-hand side is basically the work done by the applied force minus the lattice friction. And then on the right-hand side, we have two terms. This term, this first term, is due to the fact that now the dislocation is no longer straight, so it is longer than a straight dislocation, and therefore you have the line tension, this gamma, that I introduced in my slide number 1. So this is the lengthening, this is the line tension energy, if you like, for a wavy dislocation as compared to a straight dislocation. And then this second term would be the work done dissipated as the dislocation sweeps through this stacking fault area. So this is the energy balance. And then from this, you basically can divide this equation by this integral, and then this term will be related to how much stress you need to apply to move the dislocation. And it turns out that as long as I'm considering a long enough dislocation, this last term, this second term will vanish. So eventually you will conclude with this very simple formula. So here, this is the the stress due to the fluctuation of the stacking fault energy, and it can be computed by this quantity on the right-hand side. Basically, if you know the shape change of the dislocation, and you can work out the derivative of it, and then do this integral on the top, and then you do this integral on the bottom, you can calculate this stress or resistance due to the fluctuating gamma. So this equation is quite general. It doesn't involve any strong intensive assumptions, just this energy balance, which should be correct. So what is needed would be this Wy, right? Which is the difference between the shapes in the two dwell states. And then we can obtain this Wy from either MD simulation or from direct TEM observation. So of course we need input from other results to be able to do the calculation. So for example, from MD, we can obtain a wavy dislocation. Let's say we can do a Fourier series fit to the dislocation shape, and then we'll then be able to show that the equation just now can be obtained by this thing on the right, and that will enable us to calculate the strengthening due to the fluctuating fault energy. And in this particular alloy that we were looking at, that stress term turns out to be 400, 500 megapascal for different alloy conditions. So this is for the random state, and these are annealed where some short-range ordering has developed. So in this case, the strengthening due to the fluctuating gamma is pretty constant, pretty independent on the alloy state. As I said, you can also back out the W function statistically by doing a lot of weak beam imaging of dislocation morphologies in the TEM. So if you do weak beam, you would be able to understand the waviness or the shape of the dislocations very well. And then you do some digitization imaging, you will be able to back out that W function, and also enable you to calculate the stress due to the fluctuating gamma. So we have done it for different CCAs. So that's the nickel chrome cobalt, and that's another one, which is a BCC in this case. And no matter what system that we are looking at, that contribution due to the fluctuating gamma turns out to be the dominating component compared with, for example, the power stress or what we call the fissure strengthening due to the breakage of the ordering. So in this case, the red color will be what we're looking at. So in this FCC system, that will be like 60% at least. And for the BCC system, we'll be looking at this beige color, which again is the dominating component, especially for the random state. So take home number one, by analyzing the energy balance of dislocation shapes, we can calculate the strengthening factor due to the fluctuating atomic environment represented by the fluctuating gamma fault, fault energy, where this one doesn't involve any strong assumptions because it can be obtainable from purely MD simulation or TEM observed dislocation shapes. And then this term is a dominating factor, easily more than half of the strength. So the first part was on the strengthening due to the atomic environment represented by the fluctuating fault energy. Now I come to the second topic that I want to discuss today, which is the Larkin transition. This is a rather interesting, and this is a much talked about topic recently in the community, in the dislocation community. So several groups worldwide are actively looking into this Larkin regime, not necessarily for CCAs, but for general alloys as well. This is, in my mind, quite an interesting topic. So what is Larkin length? This actually is a more general concept in physics. So this is a characteristic length scale to describe how a system transits from a uniform or straight behavior to a rough, disordered behavior in the presence of some random noise. So originally, the Larkin transition was discussed in the context of pinning of magnetic flux lines in semiconductors. But more recently, due to these pioneers, Michael Sizer, for example, my good friend, 20 odd years ago, they began to consider this Larkin transition in the context of dislocations in metals and dilute alloys. So basically, the literature understanding for dilute alloys or pure, metals with some impurities would be that in the short length scale, so therefore, if you look at dislocation in a very high resolution, dislocations are mostly straight. And of course, this is due to the line tension that I talked about in the first slide. So even though there may be obstacles, local obstacles, such as dilute solute atoms, because the dislocation tries to stay short, its shape is mostly straight. But then if you zoom out and look at a very low resolution image of the dislocation, I'll give an example later on in the next slide. The dislocation will adopt a random walk or self-affine behavior. Okay, so that's better illustrated in this slide in here. So this is a typical TEM image of dislocation cluster in a mildly deformed sample. So if you pick any dislocation out, you would agree that the dislocation in this sort of kind of low resolution would be very wavy. And in fact, people have done analysis to show that this is actually sometimes it would exhibit self-affine geometry or fractal geometry or some people call it random walk. But if you zoom in a very tiny part of a dislocation, so in a high enough resolution, the dislocation line would tend to be straight. Well, this is the literature understanding, right? So that's the so-called Larkin transition. That is, if you look at a dislocation shape using different resolution scales, there is a transition from being straight to fractal-like. From high to low resolution. So that's called the Larkin transition. Well, there are a few interesting consequences from the Larkin transition. So especially if we look at the low resolution scale, so the so-called super Larkin regime of the transition. One very important conclusion is that the equipartition of energy for dislocation harmonics would not hold in this super Larkin regime if the dislocation shape is fractal or self-affine. So to show that, to prove that, we only need a few lines of math. So if you think that the dislocation shape can be represented by a Fourier series, which can be quite generally true, then the energy per projected dislocation length could be shown to be a superposition of the individual harmonic terms, where each term is proportional to this h over L, where h is the Fourier series amplitude and L is the wavelength of that particular Fourier series mode. So this h over L could be regarded as the waviness of that particular harmonic mode, because it is the amplitude divided by the wavelength. All right, so if that mode bulges out a lot, so h will be large with respect to the wavelength, so that waviness will be high, and the energy associated with that harmonic mode would be proportional to the squared of this waviness. So that's the idea. So U for a given harmonic mode I will be proportional to this waviness squared. So this kappa is known as the waviness. So if we think that equipartition of energy would hold, then this U should be the same for all I's, for all harmonic modes. Then we would require this H over L to be the same for all the harmonic modes. Or in other words, H will be proportional to L, or H squared will be proportional to L squared, or H squared will be proportional to 1 over the wave number squared, right? So obviously, as these people have shown, this condition is not held in the super Larkin regime where the dislocation shape is fractal. They have plotted h squared over the k squared, over the k in this case, and they have found that from their simulation, h squared, instead of being proportional to 1 over k squared, h squared is just proportional to 1 over k cubed. So we have this conclusion, which is in the super-Larkin regime, where the dislocation shape is non-fractal, sorry, is fractal, then equipartition of energy of harmonic modes would not hold. So with that background, we began our study some years back on a few CCAs. So these are the systems that we looked at, the nickel, chrome, cobalt, and then this 5-element high-entropy system. And again, this one medium entropy, but now with the chromium represented by vanadium. So compared with the chrome system, this is with a vanadium with a stronger pinning site due to the vanadium. And also there's another alloy system. So we ran the empty simulations as I have described. We generate a lot of dislocations, pass them through the slip plane and analyze their shapes and fit their shapes using Fourier series and back out the harmonic energies as calculated by this term. And then you with enough data, we can generate a probability distribution. So typically, we'll be using 100 dislocations from 100 dislocation cells, simulation cells, and analyze their distribution. And in particular, in all these plots, for the same group of data, we plot the results in semi-log, which is the right-hand side, left-hand side, as well as a double log on the right-hand side. So typically for each alloy system and either the leading or trailing partial, we will be looking at the Fourier harmonics from 1 to 8 or 10, okay? So they are represented by different symbols. Quite interestingly, for these two alloys, so we are looking at this one as well as this one. The low harmonics, so we will be looking at harmonics from 1 to 4, and they have long wavelengths, all right? They tend to be more linear in the double log graph. So if you look at the blue data for harmonics from 1 to 4, they tend to be more linear in a double log graph. So in this graph as well as that graph for the blue data. While for the high harmonics, therefore short wavelength harmonics, they tend to be more linear in the semi-log graph. So as you look at the red data, harmonics 5 and on, they are more linear in this graph and that graph, where we plot the probability distribution in a semi-log manner. So there is a demarcation. There is something like a Larkin transformation or transition going on here. So in particular, when we zoom in to high enough resolution, the wavelengths would be short. Then we will be looking at the high harmonic numbers. The distribution of the energy tend to be not fractal, not power law, but this exponential. Okay, so that's a very interesting observation, although it is not agreeable with the previous literature on dilute alloys. So it looks like that for these CCAs, we have a new distribution, which is quite different from the situation in dilute alloy. And also, this graph shows the remaining two alloys that we have looked at. So these two are that one and that one. And we have also these two other alloys. For these two alloys, within the length of the simulation cell, we only see the Boltzmann distribution. We only see the linear behavior in the semi-log. If you plot the data in double log, the data would exhibit obvious curvature. So all the data from low to high, harmonic orders, so long wavelengths to short wavelengths, within the simulation cell length, we only see the the exponential distribution, which will be linear in the semi-log. All right, so we are seeing a new distribution not observed in dilute alloys, which is the Boltzmann distribution. So this distribution would correspond to a linear plot in the semi-log. All right, and we know that this corresponds to maximum entropy for a fixed mean energy. So the Boltzmann distribution is based on the fact that if you maximize the entropy while keeping the mean energy, which is 1 over beta in this law in here, constant, then the distribution of the energy should obey this one. So those simulations were carried out at 5 Kelvin, so basically very low temperature. If we repeat the analysis using higher temperatures, basically, again, for every alloy, we are only seeing the Boltzmann distribution. Then we looked at the literature, and we actually discovered that other people have also observed the Boltzmann distribution. In fact, they observed the equipartition of energy. Sorry. So again, to recall, if the equipartition of energy holds, then we will expect the amplitude square of each harmonic to be inversely proportional to the wave number squared. So for example, in this reference, again from CCAs, but those are high temperature simulation. If you look at the h squared versus the k or the wave number, you do have a big regime where the slope is -2. So in this case, it's not -3, but it's -2. Although well, obviously in this case it's due to the thermal contribution, but in this another reference, this -2 slope was also observed. So we were not the only group to observe this equipartition of energy. So take home 2 would be that by analyzing the energy distributions of empty simulated dislocations in a number of CCAs, we found that the long harmonics may exhibit the Larkin transition where energy distribution is close to a power law. However, for short harmonics, we have a Boltzmann distribution, and also the equipartition of energy would hold for the short harmonics. Okay, I quickly come to my last part because I realized that time is almost running out. So based on the fact that we have this a short wavelength regime, or what we call the sub-Larkin regime, where the Boltzmann distribution is obeyed, we can discuss statistical mechanics because the Boltzmann distribution in textbook knowledge is closely related to statistical mechanics. So why StatMech for dislocations? Well, StatMech is for describing the average and spread of a large ensemble of objects, which are constantly exchanging energy within between one another. And there are some macroscopic constraints applied. So the conventional idea from Boltzmann for energy exchanges for atoms or molecules colliding, right? And we can then subject to some macro constraints such as NVT or NPT. Bending that concept to dislocations, the objects in this case obviously would be the dislocations. And you can imagine that you may be talking about a single dislocation, but it is moved to different positions on the slip plane. All right. So because of the fluctuating atomic environment in a CCA, the dislocation will be exchanging, interacting with that fluctuating environment. So the so-called exchanging energy would be manifested by that stochastic interaction. The macro constraints, which are also important in StatMech consideration, will be due to the specific average properties of the alloy. All right. So usually in StatMech, we have 2 requirements. One is ergodicity, which requires that all microstates are equally probable. that should be okay, right? Because there is no particular reason why a certain state is more probable than another, even for dislocation moving to different locations of the slip plane. The other one, which is equipartition of energy, we have shown that just now by these analysis, we have shown that this slope is obeyed, -2 is obeyed. So that was also confirmed in the sublarkin regime. So with the two conditions satisfied, we can begin to develop our StatMech theory for dislocations. So the theory, cutting a long story short, would allow a heat input. So we can be talking about high temperature situations. And then if you look at this dislocation move to different positions on the slip plane, they have different shapes. And then you can do Fourier series analysis on each of these shapes. And then we can collect the harmonic energies to form ensembles. And by equipartition of energy, each ensemble should have the same mean energy, and therefore the entire collection of harmonics should have only one beta because of equipartition of energy. So the basis of the StatMech theory for dislocation would be this unified distribution of energy, which is basically the Boltzmann energy, which of course was confirmed by our MD simulations as we have seen just now. So again, this is to show that Boltzmann distribution is observed, and it is observed not just at low temperature like 5K, but at high temperatures like 300, 700 as well. So if we look at this 1/beta at various temperatures for this particular alloy with a strong pinning atomic species, the mean energy rises with temperature, but with a rather constant slope. So we can actually break this down into two components. One is a thermal component, which is the same at different temperatures. And then the other component is linearly rising with temperature, which is our usual thermal fluctuation. So in this case, with this observation, we can argue that the mean energy comprises an athermal part, which doesn't depend on temperature, as well as a thermal part in the usual thermodynamic sense. The athermal part is obviously due to the strong locking, mechanical locking or pinning of the dislocation from these vanadium sites. And that's why this is rather athermal. For other alloys where the pinnings are weaker, we have different variation of the mean energy with temperature. So some may drop before it rises. This one we have seen before. The rise is pretty linear. Some stays constant before it rises. So it depends on the pinning, the strength of pinning in the alloys. And the last but not the least, given the Boltzmann distribution, that would allow us to develop an equation for the critical resolve stress. So the critical resolve shear stress would comprise a contribution from Fischer hardening. This is due to breakage of the short range order, as we have discussed, and usually that is a very small term. Lattice friction, that is due to power stress. But the most important of all would be this a thermal resistance due to the fluctuating fault energy. And in the case of high temperature deformation, we also would have a softening term due to thermal fluctuations. So we will now have an equation to describe the CRSS of the material based on the fact that the energy jumps would occur under a Boltzmann distribution. So with that formula, we can do some predictions or analysis. So in all these graphs, the total length of the purple plus the white would be our athermal resistance due to the fluctuating fault energy. So again, you can see that that term is dominating in all the different alloys that we have studied. So I come to my conclusion now, which is about 1 hour from the beginning of this talk, recalling that for dilute alloys, we have the Larkin transition, all right? But the transition is from, on a low resolution scale, a random walk behavior, into a high resolution scale, a straight dislocation line behavior due to line tension. That is for dilute alloys. For CCAs, the low resolution is the same. It is still self-affine, but for the high resolution, we don't have the straight behavior, but instead it is always a rough shape of for the dislocation. And then the harmonic energies, if you do harmonic analysis on the wavy shape of the dislocation, the harmonic energies would obey the Boltzmann distribution. And the strength contribution basically is related to this term, where the most important factor here is the beta. 1 over beta would be the mean energy of the harmonic, of the Boltzmann distribution. And dislocation resistance in the case of CCAs is mainly dominated by this regime, by the sub-Larkin regime. So with that, I would like to stop. Thank you for your attention.
Thank you so much, Alfonso, for the very detailed, in-depth presentation about using dislocation mechanics of a very different kind to explain strengthening in complex concentrated alloys. This is really the first time that I'm really going through this, so I guess there will be questions from many people. So I request everyone to raise their hands, and I'll call out, and then you can unmute and ask the questions yourself. Starting with Vikram. Yeah.
Yeah, thank you. It's the first time I'm hearing this also. So very interesting. I had a couple of questions. This delta tau that you're calculating, what is it relative to? Is it relative to a random distribution of atoms?
It is related to the fact that the stacking fault energy, the fault energy, not necessarily the stacking fault energy, but whichever that is against the dislocation motion. So I explained beforehand that, let's say for the leading shortly, it will be the complex stacking fault energy that will be holding the movement of that. For the trailing, it will be the difference between the APB at the end to the CSF at the front. So this gamma is the thing that we are looking at, but then this gamma is spatially fluctuating.
Okay.
So the fact that this gamma is spatially fluctuating would lead to the fact that the dislocation line is now not straight. It will be wavy, and from the fact that it is wavy, its energy will be larger than the situation when the dislocation is straight, and that would correspond to a resistance term. So that will be the tau delta gamma. So the tau delta gamma comes from the fact that the gamma is fluctuating in space. So it will be a zero term in a situation where you do not have the gamma fluctuating in let's say a pure metal. It will be a zero term.
So clearly this is related to those two integrals, the Wi and the derivative of Wi.
Yeah.
And how rapidly they change. So when does this behavior sort of, if you reduce the concentration and you go towards a dilute alloy, when is there a change in the physics? I mean, is it related to some combination of the pinning effect and the concentration?
Yes,
combination
exactly.
of the two?
Exactly, Vikram, you're exactly on that point. So in the case you have a pure metal, the gamma would not be fluctuating. It will be a flat line over space, right? So the W prime would be zero.
Right.
The dislocation should be straight or mostly straight. then this tau delta gamma should be 0. So this term would not be there for pure metals. And that's the idea of the whole analysis. So here a lot of physics are hidden in these two integrals. But instead of using a very intensive model starting from first principles, I'm hiding a lot of physics into these two integrals, basically the shapes of the dislocation. And instead of using intensive models, I use MD data or TEM data to obtain the dislocation shape to help me to calculate this the resistance term.
Okay. Just another quick question, if I may. This Fisher mechanism, you said it was unimportant, relatively speaking. But if it were in some situation, that is, you're destroying short-range order, would that lead to some sort of work softening, like you have in metallic glasses and things?
Absolutely correct. Let's say in this particular system, this is the gamma surface. And in that case, the eventual APB is not 0. Of course, it depends on the condition of the alloy. Let's say in the pure random case, it is very close to 0. It's not exactly, but I think there is a residual of less than 10. But if you anneal the alloy, so if you look at these colored curves, then some short-range order will develop, and therefore the APB trailing the entire half 110 would be larger. And if you pass the dislocation through this ordering, the fissure will be stronger.
Okay. Thank you.
Yeah, Manish Ranjan, you go next.
Yeah. Hello. This is very nice presentation, sir. And can you comment on that? What will be the typical length of dislocation in sublarking like regime in CCA most?
Sorry, I missed the question. So this is about the Larkin transition, right?
No, I'm asking about typical length of dislocation in sublarking regime.
Sublarkin regime.
Yes, sir.
So what aspect of the dislocations are you asking about the sublarkin regime?
He is saying dislocation length. What would be the typical dislocation length?
Right. Yeah. That's certainly very, very interesting. I think it depends on the alloy. So let me go back to that slide, if I can find it. So we looked at 4 alloys, right? So we look at these 4 alloys. For the first 2, well, the typical cell length in the MD simulation was 800 something, 900 angstroms. And within that cell length, half of the harmonics would fall into the super Larkin, and roughly half would fall into the sub Larkin. So within that cell length, we do have the transition at the midpoint of that. So roughly it would be like 400, 500 angstroms for the transition length scale. But for the other 2 alloys, for the last 2 alloys, we could only see the sub-Larkin. We could not see the super-Larkin. So in this case, the Larkin transition length would be longer than the cell length. So we don't know how long that is, but certainly it will be longer than this 870. So it does depend on the alloy. And exactly how, I guess nobody knows at this stage. I guess more work needs to be done.
Okay, I have another question, sir. In case of BCC CCA, how this gamma can be calculated, sir?
We use molecular dynamics, but because of the number of elements involved, I work with a group who was quite capable in using machine learned atomic potentials, developing machine learned potentials. So these were from molecular dynamics for the gamma.
Okay.
For the gamma, plots like these. So these were calculated from molecular dynamics.
Because I think partial are not like experimentally seen in BCCLI. That's why I'm concerned about this
correct.
gamma calculations.
Yeah, this discussion here is only for FCC. For BCC, obviously you don't have the partials. No, you're correct. That will be another consideration. Yeah. So for the BCC, they were looking at the half over one, so it's not dissociated.
Okay. And sir, can you comment on that in case of BCC CCA, how this pulse potential like contribute to this changing shape of these dislocations? Because you mostly talk in sense of the FCC CCA, right? Because a lot of people like cutting group, you show that they have talked about some characteristic length through which the dislocation shape can change. Can you comment on that?
You mean for the BCC?
Yeah, body centered cubic.
Yeah, and what was the question about BCC? I missed that. Sorry.
Yeah, how the pulse potentials, like the variation of pulse potential due to this, different chemical species can change the shape of dislocations. Like, does it
The
factor?
variation of the pulse potential, well, we were not responsible for that model. I think in that model, let me pull out that slide. In that model, if you read that paper, I don't recall that they specifically apply the eventual result to any particular material. So these are just trends from the model. I don't think they apply that. And actually, this one they did not calculate as well. This is my own calculation based on their equations. I don't think there is a piece of work that specifically dedicated Powell's-Nabarro model to BCC CCA, at least not quantitatively.
Thank you, sir.
Yeah.
Yeah.
Rita, can you go next?
Yeah. Hi, Alfonso.
Hi, Britta.
I think I understood some parts of the talk. So I had a question about going back to that, where the dislocation is sort of fluctuating between states, where you have
Yeah.
the W parameter.
Yes.
And I was wondering whether there is also, would there also be a temperature dependence to this shape
Yes.
that
Yes.
you get? And
Yes.
also time dependence. I mean, basically temperature and time. If you're saying that atoms segregate by diffusion,
Well, diffusion,
would
first of all, was not considered in this work. So in our MD, we did not, well, for that particular part of MD, we did not do the MC exchange. So we were not looking at dislocation, solute segregation. So the dislocation is moving in a static lattice, so to speak. For temperature, for higher temperatures, the temperature effect will be simply to shake the dislocation even more. So
even
therefore,
more?
yeah, even more than what the solute environment would cause, would do. So eventually, therefore, in the final mean energy, the 1 over beta term, we broke it down into two components. And we think that at least for this alloy, the mechanical component, which is the component due to the interaction between the dislocation and the lattice, would be this 1 over beta m. That is rather constant with respect to temperature. The other component obviously increases with temperature. So if you subject to higher temperature, the dislocation would oscillate more, and therefore the energy would go up. But in this simulation, we do not allow atomic swapping. So we are not looking
Right.
at segregation. That will be a very interesting topic to look at.
Okay. Okay.
Yeah,
Thank
I think
you.
it's also highly related to Jaya's observation from AM that there will be a dynamic segregation between solute as well as dislocation core.
Yeah, which would have its own interesting temperature dependence.
Yeah, yeah,
Right.
yeah, yeah, yeah.
Yeah.
Ankur, if you could go next, and I'll come back.
Yeah, thank you very much for your nice talk. I just want to ask you with respect to the distortion we have because of the solute environment and together with the stacking fault energy, for example. So can you comment on this, that if suppose if I may say, if you have a perfect dislocation in the distortion and then a split dislocation with a stacking fault in a distortion, how you would like to comment on probably the effect on the stresses of the glide? Is there more difficulty for the partials with the stacking fault or as compared to the glide, or is it?
I think the distortion obviously would affect both. So first of all, I think the higher the distortion, the fluctuation of the fault energy would be higher, especially if you start to have some segregation, which unfortunately hasn't been addressed in this in our work so far. So it will be up to some future work to look at that. But even for the case that the solutes are not allowed to move around, but the positioning or distribution of some of the stronger pinning sites obviously would be inhomogeneous, and therefore we would expect that this term in particular to go higher. And in fact, we can see that because from the composite, yeah. So this green data would be from nickel, cobalt, vanadium, which should be compared with nickel, cobalt, chromium. They are isostructural. Both of them are FCC. The only difference is you have chromium in one case and vanadium in another case. So the chromium would be the red circles. It drops very rapidly, while the vanadium stays strong. This one is proportional. This one is proportional to the resistance to dislocation. So that will be just the fluctuating fault energy effect. The other effect could be from the power stress as well, but we won't be able. We are not addressing that in our analysis so far. But although we will expect that the more the lattice distortion, the higher the lattice distortion, the power stress should go up.
One more query with respect to high temperature I have is that, of course, you have not addressed this in this talk, but maybe I would like to have your view. One is that when you have a simultaneous dynamic solute segregation at the faults and and also at the cotral in atmosphere, and you mentioned there that the Suzuki segregation plays the bigger role as compared to the cotral atmosphere. But can you comment also on the dynamic environment just ahead of the leading dislocations, which is evolving because of this segregation environment while we are doing testing at higher temperature? How does you visualize this interaction in that sense?
It's hard to address your question quantitatively, and that conclusion that Suzuki was more prominent was only for one alloy system. For example, I spoke to Prita on the other day, and she worked on a copper aluminum system. That was the reverse. I think she observed the other way around, which is cotral being more important for Suzuki. So I don't think that is a general trend. It very likely is material specific. It's just that in this nickel cobalt chrome, Suzuki is the major, as you can see from this yellow component, while this component is the cotral. But I don't think that is a general trend.
Okay. One last query is about that. You mentioned, of course, here the nickel is sitting on the stacking fault plane, I guess. Yes.
Yes.
So for example, if you change the environment, of course, the segregation species will change, for example, because this is more of a chemical interaction where you are stabilizing in CP phase. And therefore, can you comment also on that if you are close to grain boundary and then there is a competing mechanism, because that one is more of an elastic interaction?
Yes.
Does this will change your contributions from the Suzuki?
Well, the expectation is, yes, it should change, but we haven't done any work, so there is no concrete result from our knowledge to point to that. But from our material science understanding, yeah, any defects. So these are different defects, right? Stacking fault, dislocation core, and grain boundary or other interfaces very likely should trigger segregation.
Yeah. All right. Thank you.
Yeah. So lots of other things to be looked at as future work for CCAs.
Thank you.
Thank you for your question.
Can we go back to Manish? Do you have another question?
No, ma'am. No, sorry.
Okay, so your hand was still. Okay. So Vikram, yeah, you can go again. I think you wanted to ask.
Yeah. I just wanted to clarify this point about stacking fault energy has been brought up in the context of BCC alloys and so on. My understanding is that the magnitude of the width of the stacking fault is not relevant here. Am I right?
No, it's not relevant. No, as we calculate, for example, these contributions, the width of the stacking fault doesn't matter because it is the resistance is independent on the width.
Okay. Because
but this is FCC. So for BCC, obviously we will not be talking about the stacking fault, but we may be talking about the APB arising from ordering.
But even in a BCC material, the actual slip path it leads to some initial displacement, which is a generalized stacking fault immediately followed by something else. So it's not obvious that the treatment needs to be any different. I mean, there's no, even if the final Burgers vector is 1/2, 1, 1, 1, it's made up of individual slip movements, which are whatever. Am I right there? Or?
Yes.
So there is some stacking fault involved, or there's a combination of displacements involved in arriving at the final Burgers vector.
How should I address that question? I mean, there are lots of unusual things in a, let's say, a screw dislocation, or maybe some other dislocations in BCC as well. For screw dislocation, we know that they can exhibit pencil glide, so there may not be fixed slip plane, and the core configuration matters a lot. So sometimes they have more isotropic core. Sometimes the core could be non-planar. But for the system that we have looked at, I think the simulation was really low temperature, and it wasn't screw dislocation, if I remember correctly. And we did not subject the system to the stack mag consideration. So basically, the strengthening due to the stacking fault, so-called fault energy variation, would just be the APB.
Okay.
Trailing the dislocation movement. Yeah.
Okay. I have another question relating to the complex part and the concentrated part. If I had a concentrated binary alloy, I presume the way in which it would differ from a complex concentrated alloy is in the frequency spectrum of your fluctuations.
Perhaps.
I mean, what's the difference between let's say nickel 30% vanadium and nickel 15% cobalt and 15% vanadium? Is it just
we haven't done the rest, so I wouldn't be able to give you a definite answer. But I suppose that if you have more elements, so in the case of the complex situation, there will be more possible forms of pinning sites, different choices of atomic clusters that may be harder than others. So I would expect the fault energy holding the dislocation motion to be fluctuating more. But again, more higher or lower would also depend on the bonding. So I guess it's very hard to generalize that fluctuation.
No, I was just curious about if I have two solutes with the same interaction with the parent metal, let's say the nickel, would increasing the complexity, keeping the overall solute content fixed, make it harder, or make it, I don't know, change the effect? I mean, does it come from the magnitude of the interaction, or is it also the fact that you have more than one?
Atomic misfit is one thing that people often talk about, but also the bonding, the specific atomic pairs that are harder to shear, to crack. Well, I don't have an easy answer for that question, Vikram, until we have studied the specific material systems, gather enough data from a large database, and then we can start to come up with some analysis, I think. Like Prita, she showed me that she was studying a binary system, copper and aluminium, not exactly equal atomic, but already in her case, the Cottrell was dominating over the Suzuki. So yeah, it could be very different.
Prita, do you want to add?
No. I mean, this is something that the reviewer had pointed out to us also, because we had added this line in our conclusions saying that, look, we find that Cottrell dominates over Suzuki, and this has bearing on systems such as complex concentrated alloys. And the reviewer said that, look, I'm not sure whether you can really generalize from this. And I was not aware of Alfonso's work, but it looks like you can't.
Yeah, I agree.
Alfonso
Yeah.
and I were discussing as to why our results were pretty much opposite of each other. Whether it is the
because so many factors are different between different alloy systems. I think it's very hard to generalize.
Yeah, but it would be very interesting that, if one could come up with some sensible parameters and make like a phase map.
Yeah, that can be done after we have a lot of data on different alloys.
Yeah, and I mean, for FCC systems, that would be very interesting to look at.
Yes, I agree.
Yeah, with that, I hope all the people who had immediate questions have asked them, and I think there is a lot to mull over. I had some questions, but I'll keep it for maybe the dinner that we'll have next, Alfonso, because you're here, and it's also close to 1.5 hours now that we are all here. And I would really like to thank you once again for this amazing presentation, and also for patiently answering all our questions, and also for all the many talks and presentations we've made you give over the last 1 week. So with that, I would again announce to those who are here that there is a Structural Integrity Conference and Exhibition that is coming up in December. We have publicized it across, and we will keep publicizing it, and you're welcome to submit abstracts to that. With that plug-in, I would like to thank you all for your patience and attention, and we'll see you in another webinar, hopefully next month. Thank you.
Thank you. Bye-bye.
Bye.
Thank you for having me. Bye-bye.